All right, welcome back everybody. In this video, we are going to do some examples of using the definition of the derivative. So in the previous video, we defined the derivative by looking at these difference quotients of a function around some point A where an A coin was in the domain. And we said, okay, let's look at the limit of these difference quotients, right? So as x approaches A, what's happening to the slope of the secant line through those 2 points. All right, so let's see if we can do some examples. In fact, well, we're actually going to start with a couple of non-examples. All right, so our first non-example. Okay, so this is non-example because these are going to be functions here that are not differentiable at a point. So let's say I define some function f, and it's going to be x to the 1/3 power, which you'll recall means the cube root of x. Okay, and this function, right, is continuous for all real numbers x. Okay, that's very nice. But despite being continuous everywhere, f is not differentiable at 0. Okay, so let's see why. So I want to compute this difference quotient. Okay, so the difference quotient at 0 of f. So let's see, we know this is going to be, at some, say, some value x. Okay, not equal to 0. So here x not equal to 0. So this is going to be the value of f at x minus the value of f at 0 divided by x minus 0. Well, okay, this is easy to compute because we know what f of x is. F of x is x to the 1/3 power. And f of 0, well, the cube root of 0 is 0. So don't have to write anything. Over x minus 0, that's just x. All right, well, let's simplify this. Okay, because x is not equal to 0, we can do some cancellation, and we get this is 1 over x to the 2/3 power. All right, now, when we're computing the derivative, we look at these difference quotients, and then we need to take the limit as x approaches, in this case, 0. So the limit as x approaches 0 of the difference quotient of f based at 0 is the limit as x approaches 0 of 1 over x to the 2/3 power. All right, now what's happening as x goes to 0 to 1 over x to the 2/3 power? Well, as x approaches 0, it's either coming from the negative side or from the positive side, but I'm going to square it. That's what this 2 does. And so I don't really care if it's negative or positive. When I square it, it's positive. However, when I square a really small number, whether it's negative or positive, it's still going to be a small number. And then I'm going to take the cube root, and it's still going to be a small number. And then I'm going to take 1 and divide it by a small number, which is going to give me a big number. And in fact, as x is getting closer to 0, this number here, x to the 2/3, is getting smaller, and hence the ratio 1 to x to the 2/3 is getting bigger. In fact, this limit is infinite. And that tells me that this limit doesn't exist. Okay, so this implies that f is not differentiable at 0. All right, let's do another non-example, and then we'll finish with an actual example. So now we'll define a new function g of x, and this is one of our monster functions. So it's away from 0, it's going to be defined as x times sine of 1 over x. Okay, I could have started with sine of 1 over x, but that's not even continuous at 0. And we're going to see actually in the next video that if you have any chance of being differentiable, you have to be continuous. So this function is going to be continuous at 0. So we have a chance. Okay, so g is continuous. Well, again, actually not just at 0, but is continuous for all x. Okay. But I claim g is, again, not differentiable at 0. So again, we're going to see that by computing the difference quotient. So here we'll let x not be 0, and I'll take the difference quotient at x. So that's going to be g of x minus g of 0 over x minus 0. All right, well, g of x, when x is not 0, it's given by this top line. So this is going to be x sine of 1 over x. Okay, minus g of 0, but g of 0 is 0. So I can ignore that. Again, divided by x. Okay, well, x is not 0, so cancellation is okay. And I'm left with sine of 1 over x. Okay, but here we have this problem now. If I take the limit as x goes to 0 of the difference quotient, this will be the limit as x goes to 0 of sine of 1 over x. And we've seen before, this limit doesn't exist. As x goes to 0, 1 over x is either going to positive infinity or negative infinity. Either way, the sine function is just oscillating madly. And so, in fact, this does not exist. And so this implies that g is not differentiable at 0. All right, well, what is differentiable? Fine, let's do an example where this actually works. So we're just going to soup up our monster function a little bit. So I'm going to let h be defined, again, piecewise. So when x is not equal to 0, this will be x squared times sine of 1 over x. We'll see if that helps any. So this is when x is not 0. And again, when x is 0, we define h of 0 here, right, to be 0. Okay, so in this case, h is going to be continuous and differentiable for all x. Now, using things like the product rule and the chain rule, we're going to be able to compute an explicit derivative for h for all x. But in this video, I just want to focus again on the point 0. Okay, so let's assume x is not 0, and let's compute the difference quotient of h at x. Okay, so this is going to be h of x minus h of 0 divided by x minus 0. Okay, away from 0, h is given by x squared sine of 1 over x minus h of 0, which is still 0, divided by x. Okay, x is not 0, so I can cancel, and I get x sine of 1 over x. All right, now I want to take the limit as x goes to 0 of this difference quotient. So that'll be the limit as x goes to 0 of x times sine of 1 over x. And you may be thinking, oh, but you still have this sine of 1 over x, which is just doing all sorts of dancing, oscillating up and down. However, that x in the front will make all the difference. Okay, we're actually going to use the squeeze theorem. We know, even though it's oscillating, sine of 1 over x still lives, right, in between negative 1 and 1. Okay, so in absolute value, I know that the absolute value of the sine of 1 over x is bounded between 0 and 1. So if I multiply this inequality by the absolute value of x, which I'm doing just so I don't have to worry about whether x is approaching 0 from the positive side or the negative side. So this would imply, if I multiply by the absolute value of x, that 0 is bounded by the absolute value of x sine of 1 over x is bounded by the absolute value of x. Now, 0, of course, as x goes to infinity, or as x goes to 0, doesn't do anything. It stays 0. And also the absolute value of x as x goes to 0 goes to 0. And therefore, by the squeeze theorem, the absolute value of the product of x and sine of 1 over x also has to go to 0. But as we've seen before, if the absolute value of a function is going to 0, then the function itself has to go to 0. And so, in fact, this limit is 0, which implies h is differentiable at 0 with derivative Well, 0. And there we go. Okay, so we've seen in all of these examples that we could have continuity and maybe not get differentiability. However, in the next video, we'll show if you get differentiability, in fact, that implied you had continuity, and that's why these examples worked out the way they did. All right, we'll see you next time.